Good morning, everyone. I'm from the School of System Engineering at the National University of Defense Technology in China. It's my great honor to present our paper titled PromptER, Prompt Contrastive Learning for Generalized Entity Resolution. In the big data era, business, government, and scientific organizations increasingly rely on massive amounts of data. Data integration stands as the most usual means of acquiring large-scale datasets. Data integration facilitates the provision of vast amounts of data required for training artificial intelligence systems, helps to obtain more accurate data analysis results, and play a significant role in data cleaning. Entity resolution, also known as entity matching, aims to identify records from multiple data resources that refer to the same entity in the real world, which is a fundamental problem in data integration. For example, suppose we aim to integrate the product catalogs of Amazon and Google. Entity resolution is to determine whether the records correspond to the same real-world product. Traditional entity resolution workflow contains three main steps. The first step is schema alignment, is to align the columns to compare so that the attribute-wise similarity scores can be computed as matching features. The second step is blocking. It is to group potential matches to reduce unnecessary computations. The third step is entity resolution. It aims to perform fine-grained matching on potential matches to yield more accurate matching results. However, in real scenarios, entities can be represented in a diverse set of data formats. The job posting naturally come in a variety of formats as companies can upload plain text, PDF in the upper right, or use a template to create the job posting attribute by attribute. Some datasets collected by information extraction tools of the platforms are in structural format. We call the integration of data sources with different formats as generalized entity resolution. Due to the different data types, unifying their data schema is not possible. Therefore, we explore the use of end-to-end deep learning methods to tackle this problem. Deep learning methods have the following advantages. First, it is an end-to-end framework without complex pre-processing operations to manually construct matching features. Second, it leverages the powerful semantic understanding capabilities of pre-trained language models to alleviate from traditional character matching to semantic matching. Third, it is more robust to data quality issues, such as data missing and inconsistent data representations. Finally, it can handle blocking and matching tasks using only one model. Our proposed approach starts with a serialization step to prepare for the input of the model. Second, the prompt embedding method is applied to generate the embedding for each record. Third, in the contrastive pre-training stage, the model parameters are updated to enable the generated embedding to capture the semantic similarity between records. After acquiring the embeddings, we apply the k-nearest label method to group possible matching records. Finally, we use the labeled data to train the method, and the trained method is applied to get the final matching results. Our overall model contains two stages. The first is the pre-trained stage, and is trained with the contrastive loss to get the embedding for entities. The second is the fine-tuning stage, which uses the generated embeddings to get the final matching results. In the pre-trained stage, only the embedding model parameters are updated and the Machamp model parameters are frozen. Since pre-trained language models require token sequence as input, a key step is to convert records into token sequence. We design a serialization method that transfers original structured or semi-structured data into token sequence while preserving the structural information. For relational table, the serialization method is we add special tokens before the attribute name and the while tokens and the attribute values. Then the serialized token sequence are fed into pre-trained language models like BERT or GPT to generate their embeddings. Conventionally, the embeddings of the DOS token is considered as the embedding of the entity description. However, this embedding method suffered from the model collapse problem. That is, regress of whether the entities are actually similar, their quotient similarity is consistently high. This is because the embedding space is anisotropic in the encoding space, and the high frequency words are in the column top and the low frequency words are in the column bottom, and the embedding of the whole sequence is dominated by the high frequency words. So regardless of whether the entities are actually similar, their quotient similarity is consistently high. To address this, you can see from the picture that no matter the x-axis is the actually similarity score between entities. The y-axis is the quotient similarity between their embeddings. We can see from the figure that no matter how close is their true similarity, their quotient embedding is always very high. To address this problem, we propose a prompt-based method to obtain record embeddings. By reformulating the sentence embedding task as the pre-trained mask language task, we can effectively using original BERT layers by leveraging the large-scale knowledge and avoid COS embedding bias. We first apply a grid searching method to find the most proper prompt template. Then we use the embedding of the mask token as the entity embedding. In this figure, we can find that employing this approach allows for obtaining better entity embeddings. Similar entities have high quotient similarity between their embeddings, while dissimilar entities demonstrate low quotient similarity between their embeddings. To enable the model to better discriminate between matching and non-matching entity embeddings, we have developed a contrastive pre-training process. Hello, everyone. You can still hear from me?
Yes.
Hello? Oh, okay. I continue.
Yeah, we can hear you.
Oh, okay.
We can hear you.
Oh,
yep.
Oh, okay. To enable the model to better discriminate between, you also can see my PowerPoint. Hello?
Yeah. We can see your PowerPoint. Yep, everything's perfect.
Oh, okay. To enable the model to better discriminate between matching and non-matching entity embeddings, we have developed a contrastive pre-training process. It is to make the embeddings of the same entity description sufficiently close to each other, while making the embedding of different entities far from each other. In the pre-training process, the model is trained with the contrastive loss. In this figure, sim is the quotient similarity function. How is the temperature hyperparameter in the range of 0 to 1. For each record, the numerator calculates the similarity between the current record and its Machamp record, while the denominator computes the similarity between the current record and all other records in the same batch. To alleviate the issue of including records of the same entity as negative samples during the sampling process, we employ a strategy where negative samples are sampled within the same data sources, while positive samples are sampled across different data sources. We use a different templates to represent the description of the same entity as different points of view without changing the record itself. The method can provide diverse representations of the same entity, thereby enhancing the model's robustness. After the pre-training stage, we use the trained embedding model to generate embeddings for each entity. Subsequently, employing the k-nearest neighbors clustering method, we group potential matching entities together. The following stage is fine-tuning, during which we freeze the parameters of the embedding model and solely train the parameters of the classification head. We feed the embeddings of entity A and entity B, the subtraction of entity A and entity B into a classification head composed of a multiple perception layer to obtain a binary classification result, indicating whether they are a match or not. The next section is the experiment part. We present the results of our experiments. We use the Machamp dataset, which contains several generalized entity resolution tasks. Each dataset contains 2 data resources, which can be in one of the 3 formats: relational data table, semi-structured data, and textual data. When they are of the same format, they can have a homogeneous schema or heterogeneous schema. The following part is our experiment results. In 5 of 7 datasets, our method achieved the best results. On the other 2 datasets, our method also achieved the second best result. Among all the independent representation models, our model is consistently the best, except for the semi-test W and the real test dataset. Our closed method outperforms interdependent representation models such as DeepMarcher and D2. For the semi-test W and real test datasets, D2 achieved the best performance, while supercount and our method perform relative poorly. This is because the input record pairs contain long tests, which are relatively dirty, as they contain a lot of information that is irrelevant to the matching decision. This information also participates in the representation process and dilutes the record embedding. But supercount and PromptER heavily rely on the comparison between record embeddings, which results in a decrease in performance. The following part is the entity blocking results. All the plots in this figure show that as k increase, both record and candidate set ratio increase. Ideally, we want a high record and a small candidate set ratio. From this perspective, our proposed method outperforms supercount and SentenceBird on 6 datasets, and it achieves higher record with a smaller k value. Following part is ablation studies. We use BERT and Roberta as backbone. It can be observed that the proposed method significantly improves the performance of both BERT-based and Robert-based methods. To further investigate the influence of prompt embedding on record representation, we plot the cosine similarity distribution of record embeddings for SentenceBird, supercount, and PromptER. The result demonstrates that prompt embedding is better for distinguishing between matching and mismatching records results in better performing in entity matching and entity blocking tests. We also investigate the influence of prompt embedding on convergence speed. Our method requires fewer training steps to reach convergence compared to baseline. The above results indicate that our model requires less training time and thus reducing the time cost of model training. That's all. Thanks for your listening. Next part is